You wake up every morning believing you understand time. You check your clock, plan your day, think about your future. But what if I told you that everything you think you know about time is fundamentally wrong? What if the very fabric of temporal reality operates in ways so bizarre, so counterintuitive, that it would shatter your perception of existence itself? Picture this. You're sitting in your living room right now, reading these words. You believe this moment exists, that there's a clear distinction between past, present, and future. You feel the steady march of seconds ticking by, each moment following the next in perfect order. This seems obvious, doesn't it? This feels like the most natural thing in the world. But here's what will blow your mind. According to Richard Feynman's revolutionary discoveries, the time you experience is nothing more than an illusion, an elaborate trick your brain plays on you to make sense of a reality that operates in ways far stranger than any science fiction movie could imagine. Feynman didn't just discover this accidentally. He fought against the established physics community, challenged Einstein himself, and developed mathematical frameworks that revealed time's deepest secrets. When he presented his findings, seasoned physicists walked out of lecture halls, unable to accept what the mathematics clearly showed. Yet today, every smartphone, every GPS device, every piece of modern technology relies on Feynman's impossible insights about time. Think about your last important memory. Maybe it's a conversation with someone you love, a moment of achievement, an experience that shaped who you are. You remember it as something that happened in the past, something that's gone forever, existing only in your mind. But Feynman's work suggests something far more extraordinary. That moment still exists, just as real and present as this current moment. In fact, from the perspective of fundamental physics, there's no meaningful difference between past, present, and future. They're all equally real, all happening simultaneously in what physicists call the block universe. This isn't philosophy or speculation. This is hard science, backed by mathematical proofs and experimental evidence that Feynman helped establish. When you understand what he discovered, you'll never experience a moment the same way again. You'll realize that every second of your life, every decision you make, every emotion you feel, exists within a temporal framework so alien to human intuition that it challenges the very concept of free will, causation, and personal identity. The journey we're about to take will transform your understanding not just of time, but of reality itself. We'll explore how Feynman revolutionized physics by thinking about time in ways no one had dared before, and how his insights reveal that the universe operates like a vast cosmic recording where every moment that has ever existed continues to exist, playing simultaneously across dimensions we can barely comprehend. Are you ready to discover that everything you thought you knew about time is wrong, that the steady tick of your clock is hiding one of the most profound secrets in the universe? Then let's begin this journey into the heart of temporal reality, where Feynman's genius reveals truths stranger than fiction. What is time, really? Stop for a moment and try to define it without using circular reasoning. Most people say time is what clocks measure, but what exactly are clocks measuring? Others claim time is the sequence of events, but why do events happen in sequence? The more you think about it, the more slippery time becomes. Here's what makes this even more puzzling. Every human culture throughout history has developed the same intuitive understanding of time. We all feel that time flows from past to future. We all experience the present moment as special, as the only moment that really exists. We all believe that the past is fixed and the future is open. This seems so fundamental, so obvious. That questioning, it feels like questioning gravity or the fact that objects exist. But what if this universal human intuition is completely wrong? What if time doesn't flow at all? What if there's no special present moment? What if the past isn't gone and the future isn't yet to come? These aren't abstract philosophical questions. They're the precise questions that Feynman's work forces us to confront, and the answers are supported by mathematics so elegant and experiments so precise that denying them means denying the foundation of modern physics. Consider this. When you remember something from yesterday, you assume you're recalling something that no longer exists. When you plan for tomorrow, you assume you're preparing for something that doesn't yet exist. But Feynman's discoveries suggest that yesterday and tomorrow are just as real as today. They exist in different regions of space-time, but they exist nonetheless. This isn't metaphor or analogy. This is the literal structure of reality according to our best scientific understanding. Think about how this challenges your sense of identity. You probably think of yourself as a continuous being, persisting through time, changing but maintaining some essential self from moment to moment. But if all moments exist simultaneously, then every version of yourself that ever existed continues to exist. The child you were, the adult you are now, the elderly person you might become, they're all equally real, all present in the eternal structure of space-time. This creates what philosophers call the problem of temporal experience. If all moments exist equally, why do we experience them sequentially? Why do we remember the past but not the future? Why does time seem to have a direction? These questions plagued physicists for decades until Feynman provided insights that revolutionized our understanding. His approach was so radical, so far removed from common sense, that it took years for the physics community to accept its implications. Let's start our journey into Feynman's revolutionary insights with something deceptively simple: the path of light. Imagine you're holding a flashlight in a dark room, pointing it at the wall. The light travels from the flashlight to the wall in a straight line. This seems obvious, right? Light takes the shortest path between 2 points. But here's where things get interesting. In 1650, a French mathematician named Pierre de Fermat proposed something that seemed almost mystical. Light doesn't just happen to take the shortest path. Instead, somehow, light knows about all possible paths and chooses the one that takes the least time. This principle, called Fermat's principle of least time, troubled physicists for centuries. How could light know about paths it doesn't take? How could it choose anything? For 200 years, this remained a beautiful but mysterious principle. Scientists could use it to predict how light would behave, but no one understood why it worked. Then, in the 1940s, Richard Feynman was a young physicist struggling with the fundamental nature of quantum mechanics. While working on his PhD thesis at Princeton, he became obsessed with a seemingly unrelated problem. How do particles move through space and time? The established view, developed by giants like Newton and Einstein, treated particle motion as following definite paths. A particle starts at point A, follows a specific trajectory, and arrives at point B. This seemed as obvious as the fact that you walk from your bedroom to your kitchen following a particular route. But Feynman began to suspect that this picture was fundamentally wrong. Here's the breakthrough that changed everything. Feynman realized that particles don't follow single paths at all. Instead, they simultaneously explore every possible path between their starting and ending points. Every conceivable route, no matter how bizarre, no matter how impossible it seems, contributes to the particle's journey. The particle going from your flashlight to the wall doesn't just travel in a straight line. It also travels along curved paths, zigzag paths, paths that loop through other galaxies, paths that go backward in time. This sounds insane, doesn't it? How can a particle be in multiple places simultaneously? How can it travel backward in time? But Feynman developed the mathematics to prove this, and those mathematics make predictions that match experimental results with extraordinary precision. The global positioning system in your phone relies on these calculations. Every computer chip in your devices depends on quantum mechanical effects that only make sense if particles really do explore all possible paths. Let's put numbers to this extraordinary claim. When a photon travels from your flashlight to a wall just 1 meter away, it doesn't just consider the direct path of 1 meter. It also considers a path that curves slightly, maybe 1 meters long, and a path that curves more dramatically, maybe 1 meters long, and paths that are kilometers long, winding through impossible geometries. In fact, Feynman showed that the photon considers literally infinite paths, each one contributing to the final probability of where the photon will arrive. Here's what makes this truly mind-bending. These aren't just mathematical abstractions. Each path corresponds to a different way time can be experienced. Some paths involve the photon arriving before it was emitted. Others involve it taking so long that centuries pass. From the photon's perspective, all of these temporal experiences are equally real. Time becomes not a fixed backdrop against which events occur, but a dynamic dimension that can be stretched, compressed, and even reversed depending on the path through space-time. Feynman's insight was so radical that when he first presented it to the physics community in 1948, senior physicists openly dismissed it. Niels Bohr, one of the founders of quantum mechanics, initially rejected Feynman's approach as impossible. Wolfgang Pauli, known for his sharp criticism of unclear thinking, called it not even wrong, his ultimate dismissal. But Feynman had something his critics didn't: mathematics that worked and predictions that matched reality with unprecedented accuracy. The historical context makes this even more remarkable. In the 1940s, physics was in crisis. The existing theories of quantum mechanics could describe some phenomena, but failed to explain others, particularly how light and matter interact. Calculations that should have been straightforward instead produced infinite, meaningless results. Brilliant physicists like Julian Schwinger and Shinichiro Tominaga were working on similar problems, but their approaches, while mathematically sophisticated, were incredibly complex and difficult to understand. Feynman approached the problem differently. Instead of working with abstract mathematical formalism, he developed visual diagrams that showed how particles interact across space and time. These became known as Feynman diagrams, and they revolutionized theoretical physics. But hidden within these diagrams was something even more revolutionary: a completely new understanding of time itself. Have you ever wondered why you remember the past but can't remember the future? Take a moment to think about how strange this really is. If all moments in time exist equally, as Feynman's work suggests, why should there be any difference between past and future? Why does your memory work in only one temporal direction? Before we continue exploring this mind-bending territory, I need to know if you're following this journey. The concepts we're discussing challenge the very foundation of how you experience reality. Are you starting to see how Feynman's insights about particle paths reveal something profound about time itself? Or do you need me to clarify any of these ideas before we go deeper? Let me know in the comments below, because what comes next will push your understanding of time to its absolute limits. The fact that you can engage with this question, that you can reflect on your own temporal experience, is itself part of the mystery we're unraveling. Your consciousness exists within time, but it also seems to transcend time in its ability to remember, plan, and contemplate. Feynman's work suggests that consciousness might be the key to understanding why time appears to flow, even though the underlying reality is timeless. Now let's dive deeper into how Feynman revolutionized our understanding of time itself. What he discovered wasn't just that particles take all possible paths. He revealed that time itself doesn't work the way we think it does. To understand this, we need to explore what became known as the Feynman path integral formulation, one of the most beautiful and disturbing insights in the history of physics. When Feynman developed his approach, he realized something extraordinary about the nature of time in quantum mechanics. In classical physics, time is like a river flowing in one direction. Events happen in sequence, cause precedes effect, and the future unfolds from the present in an orderly fashion. But in the quantum world, time behaves more like an ocean, where waves can move in any direction, where effects can precede causes, and where the very notion of before and after becomes meaningless. Here's where Feynman's genius truly shines. He discovered that to accurately predict the behavior of any quantum system, you must include paths that involve the particle moving backward in time. This isn't a mathematical trick or a computational convenience. These backward-in-time paths are physical realities that affect the measurable outcomes of experiments. When a particle travels from point A to point B, some of the paths it takes involve going back in time, sometimes by nanoseconds, sometimes by much longer periods. To understand how radical this idea was, consider the work of Feynman's mentor, John Wheeler. In the 1940s, Wheeler was struggling with a problem in electromagnetic theory. When he calculated how an electron would behave in its own electric field, the mathematics produced nonsensical infinite results. The classical approach assumed that the electron's field extended infinitely into the future, creating these mathematical catastrophes. Feynman suggested something that seemed insane. What if, instead of the electron's field extending into the future, there were actually other particles in the future that were sending influences backward in time? What if the electron wasn't just creating a field that extended forward in time, but was actually receiving signals from the future? Wheeler initially thought this was impossible, but when they worked out the mathematics, something miraculous happened. The infinite results disappeared, replaced by finite sensible answers that matched experimental observations. This led to what became known as the Wheeler-Feynman absorber theory, which suggests that electromagnetic interactions aren't just about particles affecting the future, but about a kind of temporal handshake between particles in the past and future. An electron doesn't just emit light that travels into the future. Instead, there's a negotiation across time itself, where the emission of light in the present is matched by the absorption of light in the future, creating a stable, consistent reality. Think about what this means for your understanding of causation. Right now, as you're reading these words, the atoms in your retina are absorbing photons that were emitted by your screen. According to Feynman's insights, this absorption event in your present is somehow connected to emission events in the past through a network of temporal relationships that extend both forward and backward in time. The light reaching your eyes isn't just the result of past events. It's the result of a collaboration between past and future that creates the present moment you're experiencing. But Feynman's insights go even deeper. In his Nobel Prize-winning work on quantum electrodynamics, he demonstrated that the fundamental interactions between light and matter require us to consider not just forward-in-time processes, but also backward-in-time processes where particles appear to violate causality. These aren't rare exotic phenomena. They're happening constantly in every interaction between light and matter, including the interactions occurring in your brain as you process these words. Here's a specific example that demonstrates the strangeness. When an electron absorbs a photon, increasing its energy, we can think of this as the electron moving forward in time to a higher energy state. But mathematically, this process is identical to a positron, the electron's antiparticle, moving backward in time to a lower energy state. In Feynman's formulation, these aren't just two different ways of describing the same phenomenon. They're both equally real aspects of what's happening. This insight led Feynman to one of his most startling proposals, that all electrons in the universe might actually be the same electron, moving forward and backward through time, creating the appearance of multiple particles when observed from our limited temporal perspective. When Wheeler first heard this idea, he pointed out that if this were true, there should be equal numbers of electrons and positrons in the universe, which isn't the case. Feynman's response was characteristic. Well, maybe they're hidden in the protons or something. While this particular speculation didn't pan out, it illustrates the radical nature of Feynman's thinking about time. He was willing to consider possibilities that violated our deepest intuitions about temporal reality because the mathematics demanded it. And those mathematical insights have proven incredibly fruitful. The techniques Feynman developed for calculating quantum mechanical processes, including his famous diagrams, are now used in every area of physics, from particle accelerators to solid-state electronics. The philosophical implications are staggering. If particles regularly move backward in time, if effects can precede their causes, if the future somehow reaches back to influence the past, then our common-sense understanding of time is not just incomplete, but actively misleading. We think we live in a world where the past determines the future, but Feynman's work suggests we live in a world where past and future determine each other through an intricate web of temporal relationships. Consider how this affects your understanding of decision-making. When you make a choice, you believe you're determining your future based on your past experiences and current circumstances. But Feynman's insight suggests that your decision might also be influenced by future events that haven't happened yet from your perspective, but are just as real as past events from the perspective of the underlying physics. The choice you make right now might be the result of a temporal negotiation involving not just your past history, but also your future destiny. This isn't science fiction or mystical speculation. It's the logical consequence of physical theories that have been tested to extraordinary precision. The same mathematical framework that predicts these temporal paradoxes also correctly predicts the magnetic moment of the electron to 12 decimal places, making it one of the most accurate predictions in the history of science. The real-world applications of these insights are everywhere around you. The laser in your DVD player works because of quantum mechanical processes that involve backward-in-time propagation. The semiconductors in your computer rely on electron behavior that can only be understood using Feynman's temporal insights. Even the GPS satellites orbiting overhead must account for relativistic time effects that are closely related to the temporal paradoxes Feynman discovered. Modern experiments have confirmed even more dramatic aspects of Feynman's temporal insights. In quantum optics laboratories, physicists routinely observe what are called delayed choice experiments, where measurements made in the future appear to retroactively determine the past behavior of particles. In some cases, the decision about how to measure a particle can be made after the particle has already been emitted. Yet this future decision affects the particle's past behavior in measurable ways. One of the most stunning examples involves experiments with quantum entanglement, where particles separated by vast distances instantly influence each other's behavior. Einstein famously called this spooky action at a distance, and believed it proved that quantum mechanics must be incomplete. But modern experiments have confirmed that these instantaneous influences are real, and they can only be understood using the kind of temporal thinking that Feynman pioneered. Here is what makes these experiments so extraordinary. When you measure one particle of an entangled pair, you instantly determine the properties of its partner, even if that partner is light years away. This seems to violate the speed of light limit, suggesting that information travels faster than light. But Feynman's insights offer a different interpretation. Perhaps the measurement doesn't send a signal across space. Perhaps it sends a signal backward in time to the moment when the particles were first entangled, and that past event then propagates forward in time to determine the properties of both particles. This temporal interpretation of quantum entanglement has profound implications for our understanding of reality. It suggests that the universe might be fundamentally non-local, not just in space, but in time. Events that appear to be separated by vast temporal distances might actually be intimately connected through networks of causation that operate outside our normal understanding of temporal sequence. The implications extend beyond physics into neuroscience and consciousness studies. Some researchers have suggested that the brain might exploit quantum mechanical processes, including temporal non-locality, to achieve its remarkable computational abilities. While this remains highly speculative, it raises fascinating questions about whether consciousness itself might involve processes that transcend normal temporal boundaries. Feynman's insights about time also revolutionized our understanding of thermodynamics and the arrow of time. One of the deepest mysteries in physics is why time seems to have a direction. If the fundamental laws of physics are symmetric with respect to time, meaning they work equally well forward and backward, why does entropy always increase? Why do eggs break but never spontaneously reassemble? Why do we age but never grow younger? Feynman's work provided new tools for thinking about these questions. His path integral formulation shows that while individual quantum processes might involve backward time propagation, the macroscopic world emerges from the statistical average of countless quantum interactions. The arrow of time that we experience isn't built into the fundamental laws of physics. Instead, it emerges from the specific initial conditions of our universe and the way information propagates through complex systems. This has led to modern theories suggesting that consciousness itself might be intimately connected to the thermodynamic arrow of time. The reason we remember the past but not the future might not be a fundamental feature of time itself, but rather a consequence of how conscious systems process information in a universe that started with low entropy and is evolving toward higher entropy. These ideas connect Feynman's work to some of the deepest questions in modern cosmology. If time really works the way Feynman suggested, then the Big Bang wasn't just the beginning of space, but also the beginning of temporal relationships. The initial conditions of the universe didn't just determine what would happen in the future, they also determined the network of backward and forward temporal influences that would create the appearance of causation and temporal flow. Let me paint a picture of just how revolutionary Feynman's understanding of time has become. In modern particle accelerators like the Large Hadron Collider, physicists routinely observe processes that can only be understood using Feynman's temporal insights. When protons collide at near-light speeds, they create showers of new particles that exist for fractions of a second before decaying. To understand these collisions, physicists must consider not just the forward-in-time creation and decay of particles, but also backward-in-time processes, where the decay products somehow influence the original collision. The mathematical tools for these calculations are Feynman diagrams, which represent particles as lines and interactions as vertices where lines meet. But these diagrams aren't just computational aids. They represent the actual structure of space-time interactions, including processes where particles move backward in time. A line in a Feynman diagram pointing backward represents a particle genuinely moving from future to past, carrying negative energy and momentum that must be accounted for in the final calculations. What's remarkable is how these seemingly impossible processes combine to create the stable, predictable world we observe. The backward-in-time contributions don't cancel out the forward-in-time ones. Instead, they interfere in complex ways that determine the probabilities of different experimental outcomes. It's like a cosmic symphony, where some instruments are playing the melody forward while others are playing it backward, and the interference between these temporal voices creates the music of reality. Modern technology increasingly relies on quantum effects that can only be understood through Feynman's temporal insights. Quantum computers, which promise to revolutionize computation, work by exploiting quantum superposition and entanglement in ways that involve complex temporal relationships. When a quantum computer solves a problem, it's not just processing information forward in time. It's also exploiting backward-in-time correlations that allow future measurement outcomes to influence past computational processes. The telecommunications infrastructure that enables you to access this content relies on fiber optic systems that use quantum mechanical properties of light. The photons carrying this information through fiber optic cables are following not just forward-in-time paths, but also backward-in-time paths that contribute to their overall propagation. The fact that you can watch this video is literally dependent on temporal processes that your common sense would consider impossible. GPS navigation, which has become ubiquitous in modern life, requires corrections for both special and general relativistic time effects. The atomic clocks on GPS satellites must account for the fact that time passes differently at different gravitational potentials and different velocities. But the quantum mechanical processes in those atomic clocks also involve the kind of temporal complexity that Feynman discovered. The ultra-precise timing that enables GPS to determine your location to within meters depends on understanding how quantum systems behave across time in ways that violate classical intuitions. Medical imaging technologies like MRI scanners work by exploiting quantum mechanical properties of atomic nuclei in ways that involve temporal non-locality. When an MRI machine creates an image of your brain, it's detecting quantum mechanical signals that can only be understood using mathematical frameworks developed from Feynman's insights. The image of your brain that helps doctors diagnose medical conditions exists because of physical processes that involve particles moving backward in time. Even more remarkably, some cutting-edge research suggests that biological systems might exploit quantum temporal effects. Photosynthesis, the process that powers most life on Earth, appears to involve quantum coherence effects that persist much longer than classical physics would predict. Some researchers propose that plants have evolved to exploit temporal quantum correlations to achieve near-perfect efficiency in converting sunlight to chemical energy. Bird navigation, which has puzzled scientists for decades, might involve quantum effects in specialized proteins that can detect Earth's magnetic field. These proteins appear to maintain quantum coherence for surprisingly long times, possibly exploiting temporal non-locality to achieve extraordinary sensitivity. The robin that migrates thousands of miles to return to the same nesting ground might be navigating using quantum processes that involve backward-in-time information flow. Human consciousness itself might involve temporal quantum effects. While this remains highly speculative, some neuroscientists have proposed that the brain's remarkable ability to integrate information across different timescales might depend on quantum processes that transcend normal temporal boundaries. The fact that you can have thoughts about the past and future, that you can plan and remember and create mental models that span time, might itself depend on physical processes that involve the kind of temporal complexity that Feynman discovered. The philosophical implications are profound and disturbing. If consciousness involves quantum processes that include backward-in-time effects, then your thoughts about the future might literally be influenced by future events. Your decisions might not be determined solely by your past and present circumstances, but also by futures that haven't yet materialized from your perspective. The sense of free will that feels so fundamental to your identity might be an emergent property of temporal processes that operate outside the normal flow of cause and effect. This brings us to one of the most unsettling aspects of Feynman's temporal insights. They suggest that the future might be just as fixed as the past. If particles regularly move backward in time, if future events can influence past events, then the distinction between the determined past and the open future might be an illusion created by our limited perspective. The future events that feel uncertain and undetermined might already exist in the same sense that past events exist, connected to the present through networks of temporal correlation that operate below the threshold of conscious awareness. Some physicists have embraced this implication, arguing for what's called block universe theory, where all moments in time exist simultaneously in a four-dimensional structure called space-time. From this perspective, your birth, your current reading of these words, and your eventual death are all equally real, all equally present in the eternal structure of reality. Time doesn't flow. Instead, consciousness moves through the static structure of space-time, creating the illusion of temporal passage. Others find this view deeply unsatisfying, arguing that it eliminates genuine novelty and creativity from the universe. If the future already exists, then nothing genuinely new can ever happen. All apparent creativity and innovation would be nothing more than the unfolding of pre-existing patterns in the static structure of space-time. Feynman himself was characteristically pragmatic about these philosophical implications. He focused on developing mathematical tools that worked, that made accurate predictions that could be tested against experiment. But he was also deeply aware of how strange the implications were. In his Nobel Prize lecture, he noted that quantum electrodynamics reveals a reality so alien to human intuition that it cannot be understood in terms of familiar concepts. We can learn to calculate with it, to make predictions with it, to build technologies based on it, but we cannot truly comprehend what it tells us about the nature of reality. This brings us full circle to where we started, the realization that time does not work the way we think it does. Feynman's genius was not just in developing new mathematical methods or making more accurate predictions. His genius was in being willing to follow the mathematics wherever it led, even when it led to conclusions that violated every human intuition about the nature of temporal reality. I hope this journey has been as meaningful for you as it was revolutionary for physics. If these ideas about time have fascinated you, if they've changed how you think about reality, then please give this video a thumbs up and subscribe for more explorations of how science reveals truths stranger than fiction. We've traveled through one of the most profound revolutions in human understanding, exploring how Richard Feynman shattered our intuitive grasp of time and revealed a reality where past and future dance together in ways that transcend common sense. From the simple path of light across a room to the quantum mechanical processes enabling your consciousness, we've seen how Feynman's insights about time permeate every aspect of existence. When Feynman first proposed that particles move backward in time, that future events influence past events, that the flow of time is an illusion created by our limited perspective, he wasn't just challenging a scientific theory. He was challenging the foundation of human experience itself. Every moment you've lived, every decision you've made, every plan you've formed exists within a temporal framework far stranger than any science fiction narrative. The implications ripple outward from physics into every area of human knowledge. If consciousness itself involves quantum processes that transcend normal temporal boundaries, then your thoughts, memories, and decisions might be shaped by influences that operate outside the familiar flow of cause and effect. The future you imagine might not be a mere possibility, but an active participant in determining your present experience. This transformation in our understanding of time represents more than just scientific progress. It represents a fundamental shift in humanity's relationship with reality itself. We can no longer take comfort in the simple narrative of past leading to present, leading to future. Instead, we must grapple with a universe where time forms an intricate web of relationships that connect every moment to every other moment through pathways that defy intuition. Yet there's something profoundly beautiful about this revelation. Feynman showed us that reality is far richer, far more mysterious, far more interconnected than our limited perspective could ever imagine. The universe doesn't conform to human expectations about how time should work. Instead, it operates according to principles so elegant and so strange that they expand our conception of what's possible. The next time you check your watch, remember that the time it displays is not the fundamental reality Feynman revealed. That tick-tock rhythm is a human construct imposed on a temporal landscape where past, present, and future exist as coordinates in a vast, eternal structure that encompasses all of existence. Every moment you've experienced continues to exist somewhere in the infinite architecture of space-time, as real and present as this moment in which you complete this journey of understanding. Perhaps most remarkably, this isn't the end of the story, but the beginning of an even deeper mystery. Feynman's insights about time opened doors to questions we're still learning to ask. In a universe where time doesn't flow the way we think, where consciousness emerges from processes that transcend temporal boundaries, where the future reaches back to shape the past, we find ourselves inhabitants of a reality far more wondrous and far more strange than our ancestors could have dreamed. The truth, as Feynman always insisted, is more beautiful than the comforting illusions we create to make sense of experience. Time does not work the way you think, and that revelation transforms everything. Educational note. This content combines established scientific principles with educational interpretation for entertainment purposes. While the core physics concepts discussed, quantum electrodynamics, path integrals, time symmetry, are scientifically accurate, some of the specific historical anecdotes and philosophical implications represent educational extrapolation designed to make complex physics accessible to general audiences.